So we are now going to get into defining normal stresses. So when I have a material, so coordinate system, 2, 3, I have a cube. If I apply a stress to this cube that is perpendicular to the cross-sectional area on which it's being applied, then that is going to be defined as a normal stress. And the normal stress and the corresponding strain can be positive if it's in tension, as we discussed. If it's in compression, it is negative. And we are going to assume that, again, we're going to have uniform normal stress, and it's going to act through the centroid, as we've defined here, of our material. Now, this is not technically true if we take it to very, 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 very small, essentially distances or small length scales in our material. What do I mean by that? If you look right at the surface, so if I have, for example, I have a huge bar here, and if I'm looking just at like this little tiny distance d, if I apply a compressive load as we see here in the 3-3 direction, the stress is not going to be uniform in my material. So if I look at this little line here, you see that, again, I'm pressing down. There's going to be some internal force that fights against this because why? I'm in static equilibrium. That's why my forces must be equal to 0 because my material is not translating or rotating. The stress is not uniform. And it's not until we get to some kind of distance further down in the material that our stress is uniform. Now, this distance is infinitesimally small. So this is important if you're looking at, for example, if you're doing FEM analysis and grid size and those things. So this is referred to as St. Venant's principle. So this would be important if you're doing those types of operations, but for all practical purposes, when we're measuring these properties, we won't have to worry about that. Excellent. Now, normal stress. So normal stress, again, is just stress. This is our sigma, just force over area, which is going to be a Newton per meter squared, which is going to be a Pascal. Those are our units for stress. This is engineering stress because this area is the initial cross-sectional area. We'll talk a little bit about true stress. That's going to be instantaneous area. We'll talk about that a little bit later. And when we apply a stress, the material is going to deform and displace. And that is described by strain. So normal strain in this instance. So normal strain, epsilon, is defined as my final length after the load is released or after your experiment is done, minus my initial length over my initial length. What are the units of strain? Unitless, meter over meter. We don't want to give it in percentage. We have to kind of basically convert that to just a unitless value. So you can kind of see a schematic here. Normal stress, normal strain, final length minus initial length. And this should be somewhat familiar. So whether any type of engineer, hopefully you're familiar with Hooke's law, we have essentially our spring force, which is proportional to a spring constant times a displacement. You can see, every material scientist already knows this, but you can see we refer to Hooke's law as this. So I have stress, which is a force divided by unit area. Strain is my displacement normalized by itself. So this is essentially this is a spring force. This is stiffness. Young's modulus, sometimes you could see it as Y. That is essentially the stiffness of my material that I'm working with here. So this equation, this very, very simple equation, only holds for simple uniaxial stress. This equation is the most dangerous in all solid mechanics. We will almost never use this equation in our course. Instead, we're going to be using much, much more complicated notations. Even worse, actually, we'll do this. You could have an anisotropic material. 1, 2, 3, 4. Second ring tensor. You're going to be using this equation, epsilon ij equals 1 over e times 1 plus nu times sigma ij minus nu times sigma kk, Kronecker delta ij. So we're going to be using these expressions. We're going to be using second ring tensor properties. So this is the most dangerous equation in solid mechanics whenever you're looking at any material. So this does not hold for complex stress states. Don't use this equation. We'll be using and developing our own kind of methodology. So make sure that we kind of utilize this. But again, it is useful because when you basically take a stress strain curve, we are going to be using simple uniaxial stress. Simple uniaxial stress is just this. where I only have one component of stress being applied and it's normal. All right, next time we'll get into stress strain curves and talk all about those. So see you next video.